Welcome to the Explainer. Picture this. You're out on a massive steel island, hundreds of miles out in a stormy, unpredictable ocean. Dark water everywhere, absolutely nowhere to run. And you're working day and night surrounded by highly pressurized, incredibly flammable hydrocarbons. The stakes here? Unimaginably high. Survival in this environment doesn't just happen by accident. It is meticulously engineered. Today, we're diving into Module 3, Safety Systems. Specifically, we're looking at active fire protection and firefighting systems offshore. Let's get right into it.
There's a quote from our source material that really hits the nail on the head. It says, "In offshore oil and gas, fire is not an abstract risk. It's a constant, ever-present hazard." That perfectly sets the stage for what we're talking about today. We aren't dealing with a typical office building where you can just take the stairs down to the street if an alarm goes off. You're in a high-pressure zone, pulling crude oil, gas, and condensate right out of the earth. So getting fire protection right, it's not just a regulatory checkbox, it's the absolute, non-negotiable baseline for every single thing they do out there.
So, Section 1, the offshore fire threat.
You're probably familiar with the classic fire triangle, right? A fire needs three things to survive: fuel, oxygen, and heat. But look at how wild this gets when we apply it to an offshore environment. The fuel is quite literally everywhere. That's the whole point of the platform, processing crude oil and gas. And oxygen? Well, you're standing outside over the open ocean, so there's an unlimited supply of it in the atmosphere. We obviously can't remove the fuel, and we sure can't vacuum the oxygen out of the open air, so our entire engineering strategy has to pivot. We have to focus completely on automated ways to suppress that heat and isolate the fuel source as fast as possible before things spiral out of control.
Which brings us to Section 2, firewater and the ring main. The absolute backbone of offshore fire defense is the firewater ring main. Think of it as a massive, circular pipeline that runs all the way around the perimeter of the platform, often at multiple levels. It pulls water right from the ocean beneath you, using deep well electric pumps, with diesel pumps ready as a backup. But why a circular ring? Well, it's pure survival engineering. Let's say an explosion damages one side of the platform and takes out a section of the pipe. Because it's a loop, the water can simply travel the opposite way around the ring to get exactly where it needs to go. It guarantees that massive volumes of seawater are always available, no matter what goes wrong.
So how do we actually get all that water onto the fire? We use fixed water monitor stations, positioned all around the open deck areas. Honestly, they're basically massive water cannons. They can be fired up manually by a firefighting crew right there on the deck, or they can be aimed automatically by operators sitting safely in a central control room. And when these things activate, they throw a staggering high-pressure jet of water anywhere from 50 to 100 meters across the platform.
You really have to wrap your head around the staggering scale of the water volume we're talking about here to fight an offshore hydrocarbon blaze. Because when pressurized gas and oil ignite, it's not some small localized fire. It is an absolute inferno. To stand a chance against it, the active fire protection system literally has to move astronomical amounts of seawater instantaneously.
Moving on to Section 3, deluge systems and bleaves.
To really understand our next strategy, we have to talk about the ultimate nightmare scenario for any offshore worker, the BLEAV. That stands for Boiling Liquid Expanding Vapor Explosion. Imagine a pressurized gas vessel catches fire. It kicks off this terrifying domino effect. The fire starts heating the liquid inside well past its boiling point, while that same intense heat is severely weakening the steel walls of the vessel itself. It's a ticking time bomb. Eventually, the weakened steel just can't hold that expanding pressure anymore. The vessel ruptures and instantly releases a massive cloud of gas that detonates into a catastrophic, cascading explosion. It's literally the worst-case scenario.
So how on earth do you stop a BLEAV from happening? You use deluge systems. Now, these aren't your typical office sprinklers that pop one by one when a little glass bulb gets hot. Deluge systems use open head nozzles. When the main valve triggers, water violently floods out of every single nozzle simultaneously, completely drenching the equipment. And here's the crucial takeaway. The main job of a deluge system actually isn't to put the fire out. Its job is massive, immediate cooling. By completely flooding a high-pressure wellhead or vessel, it keeps that steel cool enough to hold its strength. It buys you time. It physically stops the BLEAV from happening while the safety systems automatically vent and isolate the gas inside.
That takes us to Section 4, helideck foam monitors.
Up on the helideck, the hazard profile completely changes. We aren't fighting pressurized gas up there.
we're dealing with aviation fuel. And if a helicopter has an incident, pooling kerosene burns incredibly fast. If you try to hit that with just water, you're actually going to make it worse. The water will just spread the burning liquid around. So instead, we use dedicated foam monitors that pump out AFFF, or aqueous film-forming foam. These automated systems are amazingly fast. They're designed to blanket the entire heli deck with a thick, smothering layer of foam in under 30 seconds. It completely cuts off the oxygen and seals in the fuel, killing the fire almost instantly so rescue teams can get in.
All right, Section 5, gas-based total flooding.
Let's step inside the platform now, deep into the interior, where the electrical rooms, battery rooms, and control centers are. Here, we run into a major problem, creating a clear contrast between a wet solution and a dry solution. Outside in the process areas, like we just talked about, water is our best friend. We use deluge cooling and massive water cannons to prevent explosions. But imagine pumping thousands of gallons of seawater into a room absolutely packed with high-voltage electrical panels and critical computer servers. You'd cause catastrophic short circuits and literally destroy the brains of the platform. Because of that, for these interior spaces, we have to completely switch our strategy to the dry solution, gas-based total flooding.
The way this dry gas works is actually fascinating. And the whole secret comes down to this one number, 15%. So, the normal air you and I are breathing right now contains about 21% oxygen. And at 21%, a fire is happy to burn freely. But if you can rapidly drop that room's oxygen concentration to below 15%, you cross this amazing scientific threshold. Combustion physically becomes impossible. The fire just suffocates instantly. But all those delicate million-dollar electronics are left completely dry and perfectly intact.
Let's walk through exactly how this total flooding sequence plays out, because it happens fast. First, advanced sensors pick up even the slightest hint of smoke or heat. Second, alarms instantly sound to evacuate everyone from the room, and I mean immediately. This is especially critical on older platforms that still use CO2 systems, because that gas is highly toxic to humans. Third, massive high-pressure cylinders rapidly blast modern clean agents into the space. Stuff like argonite, which is a 50-50 mix of argon and nitrogen. And finally, within literally a matter of seconds, the room is completely flooded. The oxygen levels plummet below that 15% mark, and the fire is dead before it ever really had a chance to spread. It is just a brilliant feat of automated engineering.
So, bringing this all together, what is our overall active defense philosophy? Well, you can see that offshore safety systems don't just rely on a single magic bullet. They work as a tight, sequential team. Step 1. Advanced sensors detect the hazard as early as possible. Step 2. The system automatically isolates the fuel source by slamming shut valves and blowing down all that high-pressure gas straight to the flare stack. Step 3. Deluge systems kick in to massive cool the surroundings and stop those catastrophic vessel ruptures. And Step 4. Whether it's using water, foam, or gas, the fire is aggressively suppressed before it escalates into a platform-wide disaster.
We've seen the incredible power of these automated active systems today, but it raises a pretty provocative question I want to leave you with. What happens if a fire is so intense, so violent, that even these state-of-the-art active systems are pushed completely beyond their limits? When the water pumps are totally maxed out, can the steel itself survive? Can passive structural fireproofing and specialized blast walls actually buy enough precious time for the crew to escape? Well, that brings us to the next vital layer of offshore safety engineering, and that's exactly what we'll explore next time. Thanks for joining me on this explainer. Keep learning and stay curious.